Okay, it's time to do the other way around. So from a list of terms, can we derive a general term? Okay, so there's a little bit of nuance here. So let's find what that is. So let's say we were given three terms. Let's say we were given 1, 3, 9, and then so on. So the question is, can we define a sequence? Define a sequence given only these three terms and no information whatsoever. So only these three terms. Then you're given this multiple dots to signify it goes on to infinity. Okay, so it is an infinite sequence. So can we define a general term for this, a specific general term? So let's see. So let's take a look at three um, different general terms. So we have an, which is equal to 3n minus 1, 3 raised to n minus 1. Okay, so this is a general term, right? So let's try. So since this is a1, a2, a3, so let's try if we can get these three terms using this general term. Say a1 is equal to 3 raised to 1 minus 1, which is equal to 1, right? Because 3 raised to 0 is equal to 1. Okay, that's correct. A2 is equal to 3 raised to 2 minus 1, and that is 3 raised to 1, which is 3. And then we have a3 is equal to 3 raised to 3 minus 1, 3 squared, that would be 9. So we satisfy these three terms, right? So what about a4? Let's see here. 3 raised to 4 minus 1. So 3 raised to 3, that would be 27. Okay? So we can say, so um, if this is our general term, we can say that the next term is 27, right? So let's take a look at another general term. Let's say, for example, we have so bn. So an here is not the only letter that you can use. You can also use other letters, bn. So let's say a bn, then the general term is 1 plus 2 times n minus 1 squared. Okay, so let's see if you can get 139. So b1 is equal to 1 plus 2 times 1 minus 1. So that would be 0. So this would be equal to 1. How about b2? 1 plus 2 times 2 minus 1 squared is equal to, what's this? 2 minus 1 squared. So that would be 3. Okay, how about b3? So 1 plus 2 times 3 minus 1 squared. So 3 minus 1, 2 squared, 4, 8. That would be 9. How about b4 here? You will get um, 1 plus 2 times 4 minus 1 squared is equal to, so 18, 19. Okay, so as you can see right here, so here is the thing that we need to take into account. Okay, so as you can see here, for the first three terms, we satisfy the list right here. We have 1, 3, and 9, right? And we have very different general terms here. So this means that given a list of 3 to 4 or how many initial terms, you can generate a many general terms to satisfy that initial list. But as you go on to infinity, so it will if there are different sequences or general terms, then definitely they will not be identical. But given only a few terms in the beginning, you can generate many general terms. So in fact, we can even um, get 139 if we say Cn here is equal to, we have another general term, 8n plus 12 over n minus 19. So C1 will still be equal to 1, C2 is equal to 3, C3 is equal to 9, and C4 will be 16. Okay, so as you can see here, they diverge by the fourth term, right? So yeah, so that means that the answer is no. So if you're given only these few terms, 1, 3, and 9, um, Is that enough to define a sequence? Then the answer is no. But if we change the question a little bit, let's say, um, can we define at least one? So there's the difference, at least one. So let's write that down. At least one general term that satisfy this list, then the answer is yes. Okay, so let's try that out. Okay, so we have right here example 2. Say find the general term. Find the general term of a sequence whose first four terms are 5, 6, sorry, A here is 5, 6, 7, 8, and B 2, -4, 8, -16. Okay, so what do we have here? So let's start with the first one. Start with A. So as you can see right here, 5, 6, 7, 8. This is our A1, this is our A2, A3, A4. Okay, so can we generate a general term to satisfy this? So yes. So how can we do this? We know that we need to start with 1, right? Our domain starts with 1, and then 2, 3, and 4. So we start with 5, 6, and so on. So in order to get, so in our domain, so for our first term, we have 1. So let's just add 4 to it, right? If we add 4, then we will get the first term, which is 5. And then 2, if we add 4, we get 6. So therefore, we can conclude that our an is equal to what? N plus 4, right? So let's try. So a1 is equal to 1 plus 4 is 5. a2, we have 2 plus 4, 6. So you know the drill, 7. So let's just write it down. 4 plus 4 is equal to 8. Okay, so there you have it. Okay, so that's the solution for the first one. Okay, so let's now do the second example. As we can see right here, we have 2, -4, 8, and -16. So as you can see, we have alternating signs, and this is our a1, a2, a3, a4. So the negative, they have negative signs when the n is even. A2 is -4, and 4 is -16. Okay, so let's take note of that. And if we were to disregard these negative signs, so 2, 4, 8, and 16. So how can we get this sequence right here? So if we can use, so this is an exponential, no? Exponential function, so you can raise it to n, right? You can get this using an exponential function. Say an is equal to 2 raised to n. So because 2 raised to 1 is equal to 2, 2 raised to 2 is equal to 4, 2 raised to 3 is equal to 8, 2 raised to 4 is 16. Okay, so now that we know that, how can we create this alternating signs? So here is a formula that you can memorize. So you can generate that by multiplying -1 by n, or n minus 1 or n plus 1, depending on where the negative sign lies. So as you can see here, we have our negative in the even. So let's see, let's experiment. Let's say if we were to give this -1 exponent of n. So -1 raised to 1, that would be -1. -1 raised to 2, that would be 1. Okay. So the negative is in the first term, not in the second term. And in our case, we have it in the second term. So what can we do? So what can we do with this? So we can add 1 to it. right? You can add one, let's say n plus 1. Okay, so what if we do that? So our, let's say, negative 1, so 1 plus 1, that would be, so that would be squared right there. Negative 1, and then 2 plus 1, here, negative 1. So this will definitely work, right? Okay, or you could also use, there's also another one. You can also subtract 1. You can also subtract 1. So negative 1 raised to 1 minus 1. So you will get 1. And then negative 1 raised to get 2 minus 1. That would be 1. And then with negative 1. Negative 1, 3 minus 1. To get positive again. See? So you can also use n minus 1 for this. Okay, so you just have to experiment what exponent you need to give depending on the where the negative lies. Okay, so our general formula therefore, so you can write it as an is equal to negative 1. Let's just use n plus 1 here. N plus 1 times 2 raised to n. Okay, so you can write it like that. Okay, so there you have it. So these are two examples of uh, given a list of terms, and you can construct a general term for that finite sequence. In this case, a finite sequence. Okay, so thank you for watching, and I will see you in the next video.